Let's take a look at question 8.50, which deals with addition reactions and alkenes. But before we do that, you should be aware of all of the reactions that are on this slide before embarking on the practice problems for addition reactions. So in section 8.50, it says, suggest an efficient synthesis for each of the following transformations. So what we're doing is we're going to end up converting a primary alcohol to a secondary alcohol. So if I take a look at the first set of reaction arrows, I want to convert that primary alcohol to the secondary alcohol. I'm going to have to proceed through an alkene intermediate. And the easiest way to convert the alcohol, the primary alcohol, into an alkene is to treat that with concentrated sulfuric acid. So I'm going to put concentrated H2SO4, and then I'm going to heat that up, and that's going to help to drive the water off of that. So that's an elimination reaction, and I'm going to end up with this compound. So I'm going to end up with propene. Then the next step is just going to be a Markovnikov addition of water across that double bond. The rich get richer. We follow the same rule as always with Markovnikov addition. So there's a couple of ways I could write this. I could either put dilute sulfuric acid, so I'll just put dilute sulfuric acid, because dilute sulfuric acid is mostly water with just a little bit of sulfuric acid in it. Or if I wanted to just write hydronium, I would accept that as well, because dilute sulfuric acid is mostly just hydronium ions. So if I want to go backwards, what I'm going to do is I'm going to take the secondary alcohol and I'm going to convert it into the primary alcohol. So again, the first step is going to be the same. I'm going to treat this with concentrated H2SO4, and that's going to do the elimination when I heat that up, and I'm going to end up with propene. But now I want to do an anti-Markovnikov addition of water across that double bond. And in order to effect that anti-Markovnikov addition of water, my first step is going to be to treat the alkene with borane and THF, and then in the second step to treat it with hydrogen peroxide and sodium hydroxide. So in B, I'm going from a tertiary alkyl halide to a secondary alkyl halide. So what I'm going to have to do is do an elimination and then an addition reaction. So if I take a look at the tertiary alkyl halide, if I treat this with a non-hindered base like sodium hydroxide, or let's pick sodium methoxide for fun. So sodium methoxide is a non-hindered base, and since this is a tertiary alkyl halide, I'm not going to get any substitution. I'm only going to get elimination, and I'm going to remove this proton to give me the more substituted alkene. So I'm going to end up with this alkene. So what I want to do is an anti-Markovnikov addition of HBr across this double bond. So I need HBr, and I also need peroxides. If I want to go from the secondary alkyl halide to the tertiary alkyl halide, again, the first thing I need to do is an elimination reaction. And again, if I treat it with a non-hindered base like sodium methoxide, and it could be, let's try sodium methoxide. What I'm going to do in this case is I would end up removing this proton, which would give me the more substituted alkene. So I would end up with this alkene. And if you're thinking that looks a lot like this alkene at the top, it is. It's the same alkene. But now I want to do a Markovnikov addition across this double bond. So I simply treat it with HBr. C is kind of an interesting problem in that if I treat this molecule with a non-hindered base like sodium methoxide, what's going to happen is I'm going to do an elimination. So I'd end up with this alkene. And the reason why is because if this chlorine, if this wedge is up and axial, you remember that in order to do an elimination on a cyclohexane ring, that if my leaving group is up and axial, then the proton would have to be down and axial. And we have this methyl group here, which is up and equatorial, so that means that the proton that's going down, this proton would be down and axial. So what that means is that the proton and the chlorine are anti-periplanar to each other, and we can affect that E2 elimination with sodium methoxide. So in the mechanism, the methoxide removes this proton, and we lose chloride as our leaving group to give us the alkene. The next step is going to be hydrogenation. So simply treating this with hydrogen and palladium, platinum, or nickel. I'll choose platinum as my catalyst, and you must remember that hydrogenation proceeds with syn addition. So I'm going to end up with this meso compound. In D, we have to make a cis diol. So we have to make a cis diol. So in the first step, I'm going to drive water off of cyclohexanol to make cyclohexene. So I'm going to treat that with concentrated sulfuric acid. And I'm going to heat that up, and I'm going to end up with cyclohexene like that. And in order to produce a cis diol, I'm going to treat this with osmium tetroxide and NMO.